Okay, what I've got there is a paper battery. That's the surface area, that's the size of it. Okay. I've been trying different carbons, a new one there, I haven't tried it yet, but I'll get round to it. What I wanted to show was on a very short charge, i.e. 10 seconds, kind of readopting that thing we saw with Robert Murray Smith with his paper battery. I'm charging at 4.3 volts. You've probably seen me in prior videos charging at higher voltages and all the rest of it, but I'm charging at 4.3 volts for this one. Now, there it is. There's a piece of aluminium foil there, the bits of paper, and what I'm going to do is I'm going to put this piece of graphite on top of there, like so. I'm going to put a clamp on it, like so, and hopefully we should be able to get the charge out of it. Now there's a bit of residual voltage there. I'm going to be using this 30 milliamp motor. No, it tried to spin it, but you know, it is spinning it, but as you can see, it's just a little bit of residual voltage, and it stopped. Okay, so what I'm going to do is charge that for 10 seconds. So okay, 10 seconds. We can start that now. And I'm going to run the motor and start that timer. Now, that's a brand new battery, nice clean piece of graphite, aluminium foil and a piece of paper with carbon on both sides, obviously. So if I just unplug this charger from my phone, no one's been near the power supply. There it is, 4.3 volts. We're down to 27-28 milliamps now at 1.55 volts. So that's the battery in question. That's the graphite. That's another piece of graphite. What I wanted to do was show two things: the difference between that graphite, and the difference between two different construction methods for this battery. Now I'm hoping I've got enough memory in this phone to be able to you know, get all four tests done, if you like. Turn that around so hopefully we can see it. Okay, so we're on the 2-minute mark, 1.26 volts, 24 milliamps showing on the current meter, and it's had 10 seconds at 4.3 volts. Now what I'll do is I'll be quiet and reset that one and let it run. Okay, so that was 5 minutes and 22 seconds. Now what I want to do is change that graphite for this piece of graphite, for which I will need a pressure plate of some sort, like this. Needs a bit of a clean, so I'll do that. Okay. Right, what I'm going to do is charge that again for 10 seconds. Second charge. Reset that. Same load. So all I've done basically is we've got a collector there which is aluminium, and this one is graphite, that one's graphite. I mean, that's a thicker piece of graphite, but there's nothing I can do about that because it is what it is. But it's, I mean, they look different, you know, they just look completely different. I know what the difference is between that graphite and that graphite, but well, I say that, I mean, in one respect. Now, already we're on an extra minute. I think 5 minutes 22 was the other one on that graphite there, and we've still got 0.7 of a volt. And as you can see, with that graphite we run on for a lot longer. Now, you could argue that this is its second charge, if you like. That's fine. When I show the next construction method, what I'll do is I'll run that one first and then that one, so we can negate that argument, because I know why that runs on for a lot longer than that. You know, the thickness has got nothing to do with it, it's the actual makeup of the graphite itself. Now, if I put the resistance meter on that and the resistance meter on that, they measure exactly the same in terms of resistance. I can't remember what it was. I think it was about 0.4 or 0.3 of an ohm, something like that. And it's the same with these other pieces of graphite that I've got, that I made an earlier battery from. The resistance on that is about the same. Now, that's quite thick, as you can see, but the makeup of this graphite is the same as that graphite. So anyway, we're kind of coming to a close, and we're on 8 minutes. I'm not going to stop the timer until the motor stops. As long as the battery has got some energy, the timer carries on. Okay, 8 minutes and 36. Same material, same everything, except I changed the graphites. So I'm just going to write that down. Okay. What I'm going to do is pause the video and come back in a minute when I've swapped these other two materials over. Okay, now what I want to do is show my second construction method for this paper battery. That's the piece I've just taken off. They're exactly the same size, as you can see, there's no difference. What I'm going to do, in the interest of fairness, like I said before, I use that one first for the first charge and that one for the second charge. I'm going to do it the other way around this time, so I can't get accused of not being fair. Not that anyone would, but you know what I'm going to do. Let's put that on there and that on there. There's a little bit of residual voltage. We'll check the motor. Motor won't spin. Okay, so that's essentially a flat battery. So what I'm going to do is go with a 10-second charge, still at 4.3 volts, no change, like that. Seconds. Now what I'm going to do is run the motor, run the timer, and there it is. So that's that piece of graphite that gave a better result, basically. But this is my paper battery construction method number 2, which I've sort of come up with, if you like. I had a little think about it and I think I've made it better. Now, the carbons are nothing exotic, nothing special. There's no graphenes, there's no carbon nanotubes, there's nothing like that. It's just a blend, if you like, of carbons which are readily available and sustainable, if you like. So I'm just going to let that run, and I'll be quiet, obviously, and we'll see where we go. So let's put that timer where everyone can see it. Try and put it out of the glare. Not doing a very good job. No, even worse. Okay, that's better. I did forget to add that I coated this piece of paper with this carbon, both sides obviously. I weighed it, and then I cut an exact size piece of paper and I weighed the paper to see what material was actually on there, and it is 0.2 of a gram of material. So that's 0.2, that's not 0.02, that's 0.2 of a gram. So 1/5 of a gram then. Okay, I'll let that run. It's at this point that I'm going to step back in, because we're on 9 minutes and we're already kind of 30 seconds over the previous time on this construction of a paper battery. And this is my construction of a paper battery, and I've put this carbon on first charge, and I'm going to use that carbon second on the second charge. So that should keep it fair and even, I think. So I'll let that run. I must point out, this is all the same electrolyte, it's the same charge voltage, it's the same load, the same motor. Okay, I think we're coming to an end. I must admit I've had much better times than this, but I am trialling new variations on the blend, if you like, different percentages of the carbons. So obviously I've made this worse because I've had just under 20 minutes from this, so that's, you know, on a 10-second charge. So so hopefully I can show that again at some point. At the moment I think we're going to be talking about 15.5 minutes or thereabouts. And there we go, 15 minutes 41 seconds. So I'm going to write that down. So we'll clear that. That one's clear. Take that off there. Take that off there. Put that paper back down there. Okay. We'll take that carbon away and we'll put this carbon in its place. Sorry, had to pause the video, I was disturbed. So anyway, we don't need that. So, as I said, all I've done is taken that one away and put that on there. And what I'm going to do is reconnect that. Now, these are two pieces of graphite. You can buy them on eBay. I mean, that's 1 mil thick, and that's 4 mil, I think. This is the stuff that I've been making all of my other batteries from. It's nice and thin. I like the idea of it. I'm going to get rid of it because basically I've got no control over it. It comes from China. I don't know what it is, what it's made up of, how it's made. No specifications on it whatsoever. So I'm going to be doing away with it, and I'll explain more about that later on. But anyway, back to this. We're still on 4.3 volts. Going to use the same motor. Zero that. Press those two together. Another 10-second charge. So this is the second charge then. Okay. Turn that off. Do that. And do that. Now let's see what this graphite does. It will surprise me if it gets anywhere near that, what time is it? 15 minutes 41. It could prove me wrong, I don't know, but I doubt it. So I'll be quiet and let that run. And then I'll try and explain what's going on. Here we go again. Maximum record time. Oh, that phone is doing my head in. Anyway, as I was saying, not a bad runner-up. I haven't got much memory left in this phone now at all, so we've gone from the card to the phone memory. So anyway, not a bad second place that. I did not expect that. I expected about maybe 11 minutes or even 10 minutes from that, but you know, okay, had the benefit of the second charge. Meaningless really in this. But basically, the main thing is, what's in there is my version, or a reconstruction if you like, of the paper battery. And there is a fundamental difference in what I've done and what you could do there with that piece of paper with carbon on both sides. And the difference is, and if you ask me what my technique is there, apart from this, I won't tell you. But I will say that the difference is, the fundamental difference is, the carbon surface on this battery here is highly microporous. Highly microporous. So, there is a pointer for you. Okay, and that's all I'm going to say on the matter. You've seen the times, you've seen everything, you've seen that carbon versus this carbon, and I'll tell you the difference between that carbon, or that graphite I should say, and that graphite. This one is highly microporous. Now, regardless of what you've just seen, I could just run another test now, and you know, I don't know if I could fudge a lesser time. I'm not interested in stuff like that. You've seen it as it was going, and that's it. You know, you saw the test, you saw the 10-second charge, and that come up a good second. So 14:25, 15:41 was the other time. I'm just going to write that down. 14:25. Now, with that paper there, that paper battery, or the paper that's in the middle of the battery, we got 5 minutes and 22 with that piece of graphite, and we've just got 14 minutes and 25 from my own design, if you like, on the construction. So a big leap, I think, as far as I'm concerned. I think I've got something right. I've got something wrong because I reblended the carbons, if you like, in percentage terms, and I've got a worse time with this particular one because, like I say, I've had 20 minutes from that, no problem whatsoever, from another blend. So anyway, it's the way it goes. But I think you can see, from my own perspective, that what I've done to achieve what I've got on there is highly microporous, and I believe that that means everything in what we're discussing about carbons. And I'm going to talk a little bit about the carbons in a minute. Now if you don't want to listen to me talking, end the video. That's up to you. You're going to miss a lot. It's as simple as that. So I'll shut up now, and I'll go and get some videos downloaded off this phone, so I've got more memory, and I'm going to have a chat. See you soon. Okay, so you've seen that. Excuse me, I've just literally come straight from work, as I always do, straight to this place, and I'm straight on the bench. Let's get this jacket off. Yeah, you've just seen that, and what do you make of it? Well, two things. My construction method for paper batteries is obviously better than the norm, I would say. I think I've just proved that. There was nothing magical apart from what I call microporosity, or porosity if you like, within the carbon structure. So that's all I'm going to say on that. Quite importantly, recently we've seen a video from K-Rex, where he took some sugar carbon. How he makes it, I don't know whether he makes it in a kiln or what, but or you know how he makes his carbons, I've got no idea. But zinc chloride to activate the surface of the sugar carbon. Now I've been banging on about this for a long time now, that you need to activate or reactivate your carbons, and you know I'm convinced of that, and that's all there is to it. Now the reason for that is because I think if you put it through a process where you mill this, you produce some carbon in the kiln, let's say, and you've got a nice resistance, a nice low resistance. If you then stick it in the coffee grinder or in a ball mill or whatever, my belief is you knock all the edges off it, all the sites where you need to store energy. So this is the reason why I say, and I have been saying for a while, you need to do that, and K-Rex I think proved that. I've actually done a similar test myself, run it through the kiln, zinc chloride, 500 degrees for 3 hours, and yeah, the guy is bang on, he's absolutely correct. So yeah, I was correct in what I was saying. But the other thing that activating carbons in a kiln or whatever, the reason it produces a better carbon as well is because, my belief this is, that you give the carbon some microporosity. Now that speaks for itself for obvious reasons, doesn't it? You know, you've got even more surface area then, but you can overcook it. You really can overcook that method of what am I trying to say? The activation you can overcook, and I'll explain why, or I'll try to in my terms, the way I think it all works. You've got conducting carbons and you've got non-conducting carbons. I produce some carbons in my HC chamber, my reactor, where I've come up with some lovely carbon, and it's either not that conductive or not conductive at all. So then I have to put it in the kiln, 900 degrees, 950, 1000, whatever, and I'm still working on this process, to produce the best times and whatever, all of that, to give some conductivity to your carbon. Now I'm the first one to admit this, I do not know what happens to make carbon conductive with this temperature. I don't fully understand the process yet, and I'm the first one to admit it. And if anyone can explain it to me, that's fine. If not, eventually I'll suss it out. But conductivity of carbons, graphites, whatever, amorphous carbons, a different allotrope of carbon, diamond, not conductive at all. Why is that? Why is my carbon conductive and diamond isn't? Well, it's all to do with the way the chain of atoms link together. I think diamond's 4 atoms will link themselves together. If you look at graphene, the way graphene, you've got all these atoms of carbon, and there is no what we call free electrons. Now, if my particular carbons now, what you get is 3 atoms linking together, if you like, and within that process what you get is a free electron, what they call a free electron, and it's the mobility of these electrons that we rely on for the carbon to be conductive. What is it called? What's the other word for it? A disassociated electron, I think. What is that word? Delocalized. Go away. Delocalized. Or something like that. And it's this capability for this electron to move along the carbon that makes it conductive. And like I say, I haven't quite sussed all that out yet, really. Why is it that I can heat this
carbon to a temperature and realign these atoms, you know. I'm not quite with it yet, but this is what it's all about. This is where we get the conductivity from in carbons. So looking at that then, I've said you can overcook this. Before I move on to that, you've got these bonds, haven't you? You know, these atoms are bonded, and there's that free electron that moves and produces electricity. Electron movement. It's simple. So, how can you overcook it then? Well, my theory is that if you produce a carbon with this microporosity, and you overdo it with the microporosity, i.e. you overcook it in some way or another, you break too many of these bonds, so it becomes less and less conductive. And I think, you know, this is just my theory, I could be wrong, but I think that's what will happen if you overcook it. So, you know, you've got to be careful what you're doing when you're activating carbons. There's no two ways about it. You need to activate the carbons depending upon the process that your carbons have gone through. Now, I'm not talking about graphene or anything like that. I'm talking about, you know, these amorphous carbons that I'm producing and many other people produce and all the rest of it. So that's really essentially what I wanted to try and say. So the association of this micro porosity, if you like, I've just introduced that into this battery that you've just seen running on the bench. And look at the times, look at the difference. Same size, same everything, same charge voltage, same load, same everything. It speaks for itself, doesn't it? Well, it does to me. I don't know about to you, but it does to me. That's my theory. So, and I'm sticking with that for a while. Paper batteries. I mean, I've looked at paper batteries on YouTube loads and loads and loads and loads of times. I'm just, yeah, okay, yeah, okay, yeah, I might look at that one day. Yeah, maybe I'll look at that one day. And that one day never comes. Until recently, until Robert Murray Smith did his paper battery on his bench, and he painted the carbon on, cut the piece out, well, dried it with a hairdryer. I could do that now, you know, I could do exactly the same now. But there's a difference. Now you've seen that small piece, 30 milliamps, 15 minutes, and I have had 20, trust me. If we scaled it all down from what Robert did to what I've just done, you know, 30 milliamps, he said 200 milliamps, I think it was, for 2 minutes. I kind of, in my mind, think, well, if I scale the time down and the loading up, do you know what, I'm not too far off, really. So do you know what I did? I set about. It's like, when Robert does stuff like this, it's like throwing the gauntlet down to me. You know, I'm thinking, I've got to do that, I've got to repeat that. But I tell you what, you try it. It's okay doing what I've just done there. 10-second charge. Okay, the voltage was a lot lower, I think, than what Robert charged that. I've charged it. I could charge that at 7 volts, 10 volts, whatever. I nearly lost the thread then, but I think I've got it back. You try doing what Robert did. You just try that. I.e., produce a surface area about, I think it was about that big. Right? Paint your carbons on. First charge, 10 seconds, whatever your voltage is going to be, 200 milliamp load. Now he said it was 200 milliamps, and you know what, if he says that, I believe it. You know, no reason whatsoever to disbelieve that. But you try it. I have. I've tried it. I can't get it to work. Not a chance. You know, in future, you know, I've got this data logger now, and I think that's the way forward, to be honest. But not now. I mean, you know, people have asked me why I'm not data logging and all the rest of it. It's simply because I'm still experimenting. You know, I can tell what I need to know from that motor and from the charge and everything else. I can tell exactly. I've been doing it for long enough now to know what's what. A good carbon, bad carbon, good carbon, better carbon, all the rest of it. So I know what's what. Eventually, when I settle on a particular carbon, or a blend of carbons and a percentage and all the rest of it, I will go to the data logger, you know, maybe with 1 centimetre squared, 2, 4, 6, whatever. You know, it doesn't matter. But that's when I will go to that. People have said to me, well, it's a motor and it, you know, the current diminishes with the motor. Well, we know that. And they say, well, you should use a resistor. Well, do you know what? That does exactly the same. As far as I'm concerned. I don't know about you. You know, 12 volts, a 12 volt rail, 2 1K resistors, potential divider. Measure the voltage to the middle of the potential divider, 6 volts. Use 2 500 ohm resistors, 12 volts, potential divider, you'll get 6 volts. Turn the voltage down to 10 volts, you won't have 6 volts there anymore, it'll be less. So a resistor, as far as I'm concerned, is the same. So, you know, people say use a resistor, it's no good. You need one of these, you need a constant current load, and that's all there is to it. And that's where I'll go eventually, that's where I'll be, full stop. Once I've finished experimenting, because I'm doing so much, you know, if you can understand what I'm saying there, I'm trialling that many different carbons still, and that, you know, that many different variations of these blended carbons, that it's going to go on for a while, and that's all there is to it. You know, there's nothing I can do about it. So once I settle on, as I've probably said before, 3 or 4, maybe 5, you know, best of the best and all the rest of it. And the other thing is, I keep banging on about sustainable, you know, make carbons from waste, biomass waste and all the rest of it. One of the best carbons I've produced was that garlic carbon. But you know what? Where's that actually going to go? Because as far as I can see, who in the right mind would go out and buy loads of garlic and carbonise it? It's so expensive. Well, it is in the UK anyway. So it's, you know, although it's good, you've got to look at the reasons maybe why it's good. And I do know why it's good. And it's all to do with sulphur, especially on the cathode. So yeah, what's the next best thing? Well, the apple, that was good. That was very good. Sustainability, let's see. Apple waste, yeah, I can see that. You know, and it'll almost be free. You know, they'll give you the stuff if you like. So that's where you've got to be. And that's, you know, kind of where I'm heading with these carbons. I mean, there's lots of stuff we can look at that's going to be waste and free. You know, people just want to get rid of this waste, and if you carbonise it and it works well, that's where I want to be. So I'm hoping that I haven't gone on too much, but it's all part of this world that I'm in at the moment, and it all means a lot to me. All of it, you know, everything I've just talked about means a lot to me. So I'm sorry to sound, you know, quite passionate about this tonight, but I am, you know, that's the way I am about this. I don't want to, at the moment, look at graphene. I don't want to look at graphene. We know what graphene can do. I don't want to look at carbon nanotubes. It's all like, that's all out there, you know, and I'm sort of over here, you know, producing carbons from biomass and waste. It could be anything, any kind of waste that, you know, like I said with the garlic, if you've got to go out and buy it, you know, then I can't see in my mind that there's going to be any garlic waste out there. That's the point. Onions, onion was the next best, a good one, but that again, onion is full of, well, sugars, as we know, but also a high sulphur content, so that's why the garlic is as good as the onion. I haven't checked out the apple side of things so much just yet, but I will. But you know, let's say a failed crop in an orchard that was full of bugs or whatever, I don't know, that couldn't be used, or apple cores, you know, waste, apple waste. I can see that one, so that's where I'm coming from. I think I'll leave it at that for now, because I think I'm going on a bit too much. I'm getting all passionate about it again, and you know, well, you should be, of course, but I'll speak to you later.